Hello physicists! Last video we talked about applying the kinematics equations in several scenarios. But in this video we're going to be discussing a very special scenario in which you can apply the kinematics equations in order to solve more real-world problems. We were already solving real-world problems, but this one we could actually physically see. And that is the concept of free fall. As a concept of free fall. And in free fall, you are you're accelerating under the influence of the force of gravity. And we're going to be talking more about that in a later video, but we're going to be looking at free fall. When an object falls, gravity is obviously pushing it down. And for the sake of simplicity, we're going to ignore air resistance. Air resistance does exist, but if you manipulate the equation to account for air resistance, they become very complicated. So we're going to neglect air resistance for now. And we're going to just be investigating gravity. So gravity points downward toward the Earth. So the acceleration will be downward. And we have a special symbol for the acceleration due to gravity, and that's g. G is the acceleration due to gravity. And on Earth, g is equal to 9.81 meters per second squared. Okay, so the magnitude of g is 9.81 meters per second squared. In these problems, we'll usually take the negative since g points downward, and by convention, downward is usually negative. And you can see using like vector notation that we usually use downward as negative. So the magnitude of g is 9.81 meters per second squared. And using this number, we can actually solve a lot of problems involving free fall just using this one number. So, and what's remarkable about g is that g is the same for any object. I don't care if it's a piano or a rock. When dropped from a vacuum, they will all fall with the same acceleration, g. Okay, it has nothing to do with mass in a vacuum. And I say in a vacuum because air resistance, there are lots of factors: air resistance, shape, mass, etc., etc. But in an ideal vacuum world, they will follow the exact same acceleration g. So we're going to use g as the acceleration for all free fall problems, regardless of what the object is. Okay? And free fall problems are the exact same thing as normal one-dimensional kinematics problems. We just have a fixed acceleration. So let's look at a problem. So let's say you're on a building. Okay, this is you. And you're on a building and you are throwing a rock. Okay? You're just dropping a rock. Okay, you decide to drop a rock and you want to determine how long it will take for the rock to hit the ground. Okay? So you're on top of a building, and the building, let's say it has a height of 30 meters. So a modestly sized building with a height of 30 meters, and you're on the roof and you want to drop a rock from the top. So how long will it take for the rock to fall to the ground? Now, let's write our kinematics equations. And let's see which one is best. Now, in the first equation, we don't have any information on VF. Okay, but you know what? Let's solve for VF afterwards. Okay, we don't have any information on VF initially. So if we look at the second equation, we know delta x, that's 30. We know we know V naught, that's 0, because we're just dropping it. So it starts from rest. We're trying to solve for t, and we know a is equal to g. Okay, so let's just rewrite this as V naught t plus 1/2 gt squared for free fall. Okay, and V naught t is equal to 0, so it simplifies further. Now, we have delta x equals 1/2 gt squared. So if I were to solve for t, I would multiply both sides by 2 and divide by g. So we have t and then take the square root. So if t equals the square root of 2 delta x over g. All right, that's good. Now, delta x will be negative. Delta x will be negative because if you were to think in terms of vectors and the bottom is the origin, then you're starting with a vector here and you're ending with a vector here. So there has to be some negative, some subtraction happening. So the change in x will be negative. So it'll be negative 30 rather than positive 30. Okay, and you'll see why positive 30 doesn't work, because we already said we're going to use g equals negative 9.81. So if you use positive 30, then you'll get a non-real answer. And we usually don't like non-real answers in real motion problems. Okay, so what we're going to do is we're just going to substitute everything in. 2 times negative 30 meters over negative 9.81 meters per second squared. That's kind of it, right? We've just solved this equation for t, and we get a tangible value for t. So if I were to plug in on my calculator 60 divided by 9.81 and then take the square root, we get 2.473 seconds. So it'll take about that much time for the rock to completely drop. Now, that's our first answer, 2.473 seconds. Now, what is the final velocity? So what is the velocity of the particle right before it hits the ground? Like at the instant it hits the ground, what is the velocity? Now we get to use the first equation because we've just found out t. So because we found out t, we can actually substitute. There's no algebra required because we've already solved for VF. So VF equals V naught plus AT. So V naught is 0 meters per second plus GT. So 0 meters per second plus negative 9.81 meters per second squared times 2.473 seconds. So we get negative 9.81 times 2.473, negative 24.3 meters per second. So I would say that it's going at least 40 miles per hour, the rock, at least. Just an estimate. So the rock's going pretty fast by the time it heads downward. But let's ask a harder question. Okay? So if you're doing like a problem solving session, this one's the worst case scenario. You're on the building, the same building, 30 meters. You're on the building and it's 30 meters. Now, let's say you throw it up. You throw it upward and it's going to go up and it's going to fall down. Okay? So it goes up and you give it initial velocity. Let's make it 7 meters per second. Okay, so you have a good arm and you throw it up with 7 meters per second initial velocity. So now I have a whole lot of questions. All right, so question number 1, what is the maximum height? Because it will go up to some height above the ground and fall back down. So what is this maximum height that the ball reaches? So if I want to find the maximum height, let's write down our equations. We write down our equations, we immediately see that we don't have a lot of information. We don't have a lot of information. But if we don't have VF, although we can obtain it using some thought, I'm going to explain that later. But seemingly we don't have VF. We don't have, we have acceleration, but we don't have time. And we don't have delta x, because that's what we're trying to find. So what do we do at this point? We have a lot of variables stuck, but just imagine when a ball is being thrown up, what happens at its maximum? Because you have to remember, the ball always experiences a negative acceleration g. So when it's being thrown upward, it will slow down, but at this point, the position is momentarily not changing, which means its velocity there has to be 0. It just has to be 0. And it makes sense because it's becoming more negative. And by the time it reaches here, the velocity becomes negative. So at some point it has to reach a 0, and it's at this maximum height because there's no change in position. And here's a misconception that a lot of people make, and it's that there's no acceleration when an object's not moving. That's not true. At every point, there's an acceleration of g when it's in the air, even when it's stopped. So that allows us to use these equations because the acceleration is constant throughout the entire interval. So what we can do is first solve the subproblem of finding how long it will take for the rock to reach its maximum point, and then from there we can build on the maximum height. So let's solve for the time. So VF will be 0. So VF will be 0 meters per second equals V naught, 7 meters per second, plus negative 9.81 meters per second squared times T. Okay, so we have this equation, and it's a linear equation, so it's very easy to solve. Remedial. So it should be trivial to solve this equation, and solving it gives you t equals 0.714 seconds. So we have time equals 0.714 seconds. So that's how long it takes for the rock to reach its highest point. So now that we know the time, we can substitute in our second equation. V naught t plus 1/2 at squared. All right, that's good. So we have V naught is 7 meters per second times 0.714 seconds plus 1/2 9.81 meters per second squared times 0.714 seconds squared. So let's just plug everything in. So 0.5 times negative 9.81 times our answer and square that. And we get 2.497 meters. And this kind of says, like, wait a minute. We start at 30 meters. Why do we get 2.5 meters? But you have to realize, this is delta x. This is not the actual height. This is delta x, the change in height, the change in position. So in reality, that means that we have traveled upward 2.497 meters. So the maximum height above the ground will be 32.497 meters. That will be the highest point of the rock's path. That will be the highest point of the rock's path. Okay, and now the total time. The total time to reach the bottom. And there are two ways to go with it. We're going to do the long way because it's important when you don't have these other steps to find out how you can use the initial values in order to solve for the total time. And this one will be a pain because we actually have an initial velocity. So let's work this one out. So we have delta x. We're going to use the second one because we don't know the final velocity over here. So we're going to use the second one. V naught t plus 1/2 at squared. However, V naught is non-zero, meaning that we're going to have a quadratic, which, like an actual quadratic, which we're going to have to solve with the quadratic formula, which is not necessarily the best thing to work with, but it is necessary to solve this problem. You cannot solve it without it. So our delta x will be negative because we're going downward. So we have negative 30 meters equals 7 meters per second in the positive direction. T plus 1/2 negative 9.81 meters per second squared. T squared. Okay, so now we get to use quadratic formula. T equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. And now, instead of a, b, and c, we just put these values. We have negative 7 meters per second plus or minus, and plus or minus the square root of b squared, 7 meters per second squared, minus 4a. Oh, what am I doing? 4a c. And note that c is positive since we have to solve this for 0. So just to avert confusion, this is c. So negative b plus or minus the square root of b squared minus 4ac. All of that over 2a. And then we just solve. We just have to work this all out on a calculator, and it will take quite a while for me to put all of these computations in, but I'll try not to screw up anything, because it'd be quite embarrassing if I did. Okay, now we're going to take the square root. All right, so we have two answers. Time could equal -7 plus, let's use parentheses. Okay, -7 plus this over -9.81. Note that the 2 and the 1/2 cancel. And then we get -1.86 seconds. So, that makes no sense. So we're going to use the other value. We're going to use the minus. Minus this over -9.81. And then we get 3.28 seconds. 3.29. A little more exact. So we have two solutions. This one obviously makes no sense because time is never negative, because negative time makes no sense. So if we were to compare with our first answer, just dropping it, we have 2.47. So it's reasonably correct since this time is bigger. We threw it up, so it should take a longer time. So our real time is 3.29 seconds. And that's how long it will take. So that's how you solve free fall problems. You just replace all the values with of A with G and use the two fundamental kinematics equations and properties of free fall, such as, velocity 0 at the top, acceleration is always g, in order to solve for quantities such as the maximum height and the time. Thanks for watching. If you have any questions, just let me know in the comment section, and see you next time. Bye.